Awesome. Well, welcome to 2026. If you're just tuning in, this is Re3D's attempt at helping corral the pioneers in the what we call the FGF or the pellet printing space. No, you are welcome to listen, participate, or present, whether or not you have our Gigabot X pellet printer. We hope this is just a meaningful place to build community and we're going to go ahead and post this recording at the end online if you jump off late or have to jump off early. As always, if you're interested in presenting or if you know someone we should reach out to who's doing cool things in the community, please let us know, and we're happy to see if we can't wrangle them as a speaker in future months. But this month, we're so honored to actually feature. Full disclosure, they are a customer of ours. It's Lamar University. They've had a Gigabot X for a while now, and I've been doing some really fascinating research. Today, we're honored to have Sajedul online, who is going to share a little bit about what his focus has been. He is a very established education professional, holding both a Bachelor of Science as well as a aeronautical engineering degree from the Military Institute of Science and Technology. And then he went on to get not one, but two masters, one from Utah State University. He has a Master's of Science in Mechanical Engineering, and as well as just wrapping up a Master's of Engineering Science with a perfect GPA at Lamar University. His thesis is on the characterization of mechanical performance and fracture behavior of thermoplastic PETG parts fabricated by FGF 3D printing. So he couldn't be more relevant to a lot of our interests. And so with that in mind, I'm going to turn it over to him to share what he's been working on.
Hi, I'm Sajedul Sakir. I'm presenting today the work we are doing in our lab. So it is the effect of extrusion flow rate and the print speed on the geometric accuracy and tensile strength of parts fabricated by our PETG by FGF the Gigabot X2 printer. So I am on presenting on behalf of our group. So the presentation outline, so it is like we will go to the background of the PETG and the FGF 3D printer, and then the objectives, what we are doing on in our lab, the setup we are using, and the materials and methods. Then I will show the results, what we have done in our lab and the current research, what I'm doing on, and then the discussion and the conclusion and future works. So this is the thesis paper from our lab mate Moment Shahriar. He has been graduated last year, and some parts of the presentation work will come from this thesis. And in the right figure, this is the Gigabot X2 3D printer, which is in my backside. If you see, this is the printer. So I'm going through now. So why we are using the large scale pellet 3D printing? So it is like the FGF method. It has the large scale and it is cost effective 3D printing, and PETG pellets, which are it's kind of like a recycled material coming from some industrial waste. We can use it, and there are some limitations in the filament based printers. So that's why we are using the pellet-based 3D printing by using the FGF method. So there are few challenges here. So it is like the flow control, like the extrusion flow control in the printer, and the accuracy and the strength. So I will show some of this, like what we are doing in our lab. So what problems I'm solving in our lab right now. So it is like the software defined extrusion flow rate. It is not actual material extrusion flow rate, what we are doing in the experiment. So I will quantify how the experimental and software different extrusion rate varies. And then based on the extrusion flow rate and print speed, we have printed some parts. I will show the geometric accuracy and how we can improve the dimensional accuracy of the parts. And there are some mechanical testing we are currently doing in our lab. So I will also show some results from that. So this is the Gigabot X2 3D printer. in our lab, the specification is manufactured by RE3D, and the dimensions here, the build volumes, it is a big printer. We can print big pieces here. The extrusion drive, the single screw pellet extruder. So I believe most of the people in this presentation, they have no knowledge about it because they are coming from the PETG, RE3D. And this is actually the specification for Gigabot X2, what we are using. So maximum extrusion temperature 270. The nozzle size is big here, so I'm using in between one of them. And the hopper capacity is 7.5 kg, and the power requirement is 1000 watt. And there are different kinds of material can be used like ABS, PLA, and I'm using the rPETG.
Awesome. That's awesome.
So our methodology for our lab work is like first we have selected the material, then we are doing the CAD modeling in the Fusion 360, and then we are printing the samples with the printer with different parameter like print speed settings, extrusion flow rates, and the temperature of the different extrusion temperature like bed temperature and other temperature settings also. And then we go through the dimensional accuracy, and then based on it, I'm doing some tensile testing, and then there are some analysis going on. So these are actually the methodology what we are doing in our lab. And this is the pellet, the PETG pellets, its properties and the conditions, how we dry it. So the PETG pellets has the physical property of bulk density 0.9 kg per meter cube. Then its mass and thermal properties. So it's all coming from the PETG manufacturing this recycled pellets. So we are finding this the maintain temperature 220 degree and 245 degrees Celsius. Mechanical properties of the PETG. rPETG, it's tensile strength 14.7 to 38.6 megapascal, and elongation at break 1.2 to 4.3%. And how we are before printing. So if you see the here, so we have to prepare it. So first like the PETG, and we have to go through the printing. So we have to prepare it. So for this, we have to dry it. So we are using a vacuum oven. The temperature setting is like 65 degrees Celsius, and we are drying it 12 hours, and the pressure is 0.67 kilopascal. So on that setting, we are drying the pellets for the removal of dust and most dust and contamination, and dry the pellet because there are some moisture content in the pellet, so we have to dry it before it going to the hopper of the printer. So the printing parameter we are using here, the nozzle diameter is 1.75. So I already in the specification slide of the Gigabot X2, there are different kinds of nozzle diameter like 0.4, and it is a big so it's a big printer, so it has different diameters. So I for our lab, I'm using the 1.75 nozzle diameter, layer height 1 millimeter, outline like when we are printing, there are some skirt outline is five things will print like. And then the bottom heat temperature zone is 220 degrees Celsius, middle heat zone 210, top heat zone 200, and the bed temperature is 75. And for the fabrication part, we are printing on three print speed, 3 millimeter per second, 7 and 10 millimeter per second. The travel speed, it is 100 millimeter per second in the XY direction, and the travel speed in the Z direction is 12 millimeter per second. The extrusion multiplier, we can vary it, but we are using like 1 multiplier 1, sometimes 1.2. That's why it's varied. And the infill pattern, we are using rectilinear right now, and we also try for other infill pattern. And the infill density is 70. And sometimes I also try 80%, 90%, and 100% also. And the size of software we are using in Simplify 3D. And actually the control parameters, like what we are changing. So extrusion flow rate, it is basically changed based on the print speed. So we are changing the print speed and making all other parameter same to see the characteristics of the how the printed part behaves. So before that, what I have done the experimental and software-defined extrusion flow rate. So how the software-defined and experimental flow rate, is it actually the same or not? So what I have done here, so I have used the density measurement by using Archimedes principle. So based on this formula, so actually the A is the sample what I have printed. I am taking the mass in the year, then taking the sample to the water for measuring the density based on water density. So based on this, it is actually this is the water density we are using in this formula. So the part I have printed, then I measure it in the year uh, in the measurement device. So I got it this 0.9787, and then on the water it's 0.2211 gram, all are in gram. Then from this formula I got the density is of the sample is 1.288 gram per centimeter cube. So this is actually the density of the material. What I have, something like I printed one kind of layer, like it is a big like something like only one layer, two layer, six layer, very small piece for measuring this density in the device we have in our lab. Then I measure the volume of it. And when I'm printing it in the printer, I take the time calculation, like the printing time. Based on this, I got the experimental flow rate, this. And when I was printing it, I keep the pre-defined like simplified 3D values when I'm printing it. So based on this formula and this parameter like extrusion watt 2.1 millimeter I have given in the simplified 3D, layer height 1 and printing speed 7. Based on this, I got this like 14.7 from the software, and from experimental, our density-based measurement, I got 14.57. So if we do the percentage of like really values from the software and experimental, it is almost like 88%. And I also have the like here I'm showing only the 7 millimeter per second printing speed. I also do it for other like 10 millimeter per second printing speed. So it is relatively similar, like 92%, 93%. So I'm only showing here the one kind of experiment what I have done. I don't show the all. So based on this, so it is almost 88 to 95%. The software based extrusion flow rate is uh, much more, but experimental is less, like 90% of the software, 90%, 95%. So here it is the 88%. Then uh, then what we've done, we have done the printing of the sample, like cube. So we have done a test geometry sample printing here, and then how we did. So we choose a cube. So it is simple and symmetric, and it has the accurate dimensional measurement, and it will isolate the effect of printers on quality. So we choose a cube for printing. Then we label the cube, all of the six surfaces, like different, like front face A, top face B, then bottom face E, and all of the remaining places in the clockwise direction C, D, F. And what we are doing after printing, so we are taking it like permanent marker. After immediate removal, we are marking all of the faces for our identification. And the cube we have used for the dimension of the cube is 1 inch, and it is uniform dimension. And we have printed 165 identical samples in this printer. Then we have done some like accuracy evaluation of geometry. First, the top face symmetry, like when we are printing a cube, so how the face are symmetric or not. So we are measuring it by uh, this formula, like the basic geometry formula, like the Heron's formula we are using, perimeter. So if you see here, so I have we have two triangles here. So one of the triangles area is A1 and one is A2, and P1 is the top face symmetry parameter. We defined it like the divided one area divided by the another area, like A1 divided by A2. So when A2 is higher than this formula change. So these are the formula we are using. And the properties of P1, it will be from 0 to 1. And if P1 is 1, so that means the top face, like the face we are measuring for the area, is perfect top face, like symmetry. And if it is lower, so then it means there are some distortion on the surface and asymmetry. And P1 is unitless parameter, that is like area by area. So this is the curve, what we have got from the experiment. So P1 is the top face symmetry. So if you see the curve, like it is a flow rate versus the top face symmetry P1 parameter. And flow rate is basically coming from the print speed. So so we have printed it for three print speed 3, 7, and 10. And if you see the figure for 3 millimeter per second it is from 0.65 to 1. So it is actually the color is blue, 0.65 to 1. And it is very varying from very wild varying here. And another in this flow rate, like 3 millimeter per second, we will get the flow rate. That flow rate, no print failures were observed. But when we're increasing it like 7 millimeter per second, the flow rate changes. And if you see here, it's from 0.85, the orange dot here, the orange dot. Yeah, it's okay. I have checked the comments. So decimeter, okay. Okay. 7 millimeter per second print speed. So we got it from 0.85 to the orange one very tightly clustered. So in these settings, we got the both successful and failed prints within a similar P1 range. And when we increase the print speed from 7 to 10, then the print flow rate also changes. But it's almost like if you see the yellow dot values here, they are actually near the 0.1, like 0.95 to 1. So in this range, height of face symmetry occurs, but it does not guarantee that the print is successful, like the structurally. So based on this, our results, we can overall we can say that the increasing print speed improves the surface level symmetry, but the improvement does not guarantee that the correlation does not correlate that the structural is so much stable. Then we have done another geometric accuracy evaluation by using the overall spatial or volumetric symmetry. So it is accessing through the entire cube volume. If you see here, there are lots of like part 1 and part 2 for we are using these formulas. It is actually the Heron's formula, but for the volumetric symmetry, we are changing the parameters for finding the A1 like area. And okay. And based on this A1, A2, B1, B2, so we have part 1 and part B and part A and part B for these two formula use. So we get the K values for P2, like overall spatial symmetry calculation. We have the K1 to K8 value for the P2. Like it is actually the P2, but it will varying from P2 like K1 to K8. So here it is also from 0 to 1. So if P2 is 1, it is volumetrically perfect. Lower P2 means like Okay, I will answer the questions later. So lower P2 is increasing global geometric imbalance, and it is also a dimensional parameter. So I am showing the curve from the lab we have got. So if you see here, so we also have the P2 value from it is from started from 0.93 to 1, indicating strong global geometrical balance. But at the lowest speed, when it is 3 millimeter per second, uh, all samples are successfully printed, demonstrating that the slight variation in volumetric symmetry are well tolerated at low speeds. But when we are changing the speed for 7 millimeter print speed, sometimes it fails, sometimes non-fail samples show similar kind of range P2 values. But when we are changing it to the 10 millimeter per second, that then P2 values remain very close to 1. This confirms that the global geometry symmetry is preserved despite structural failure. So that means the P2 is also like P1, structural failoring happening, but the geometric symmetry is okay. So overall, it can we can show that we can say that the highest minimum P2 values are observed in failed samples, also indicating that the print failures does not originate from the volumetric geometric imbalance. And P2 is effective in quantifying 3D geometry symmetry, but cannot be used as a standalone indicator of print success or failure. So, so P1 and P2. Now I am going through the tensile testing. What I am currently doing. So I have chosen so our lab has chosen the ASTM and D638 Type 3 as the printer nozzle diameter is high, so we have to use this Type 3 sample. So what we will do now, we are actually doing it. I'm doing it actually now. Like I'm doing some tensile testing of the samples I have printed, and this is the CAD model of the Type 3. So here the wide and thickness, it is basically from this side, like 57 millimeters, the length, this length, gauge length. And we are using the wide is 19, like we have modified the sample. So it is actually, if you go to the ASTM D638 sample, its dimensions are less, but we are modifying it because our printer diameter is much higher. If we use the standard dimensions, then the shape we got from the printing, it's not accurate for, like, it is not good for, it is very thin to go for tensile testing, and it's even break when I'm printing it. So that's why we have modified this sample length, and it is actually we modified the thickness 10 millimeter, and also for tensile strength measurement we also changed the overall length also here. So I'm showing what I'm doing now. So these are the samples I have printed from these settings, modified sample from. So, and I'm doing the tensile testing currently doing. So I still ongoing. So I can show some results like what I'm doing. So this is the results when I'm doing the tensile strengths for printing speed 7 millimeters per second. I have printed 3 samples, and then doing the load versus elongation curves. And I'm doing the current analysis of it, so it's still ongoing. So I didn't have finished. So I just show like what I'm doing in our lab now, right now. And from this presentation, so what I have, the discussion part is like software extrusion settings are not uh, insufficient. Like we have measured it. Like we have measured the experimental flow rate and software extrusion flow rate. It's almost 90% to 95% range. Although there are some mismatched when I try to when I was first started, there was so much difference, like 50% from the experiment I got some 50% result, but now after modifying the settings and everything, it's showing like the 80% to 90%. But when I started, I faced lots of difficulties, and there are so much mismatch between the software defined and actual extrusion flow rates. And then we do the density based measurement for improve the accuracy, like how it works. And based on the results, our from the lab, it shows that there are some optimized between the print speed will enhance the accuracy of the dimensions of the print and also the strength. Like strength is my, yeah, like what I'm doing now in the tensile testing. And flow rate and speed coupling is very critical in this printing. And infill density also significantly affect the tensile state behavior. What I am currently working on it, but I don't show that like how it works here because it is ongoing still. And the future work is like extrusion flow rate and print speed significantly affect the accuracy of the print samples and the strength of the samples. And optimization is required for the dimensional fidelity and also the tensile strength. And future work is like what I'm doing, like mechanical testing and the microstructure analysis. And thank you for your time. If you have any questions.
Thank you for the awesome talk and for answering the questions that were popping up in real time. Does anyone else have any questions while we still have the recording on? Oh, Christopher Papadopoulos.
Yeah, I have so yeah, there are some text messages there, so I missed the decimeter term when I'm making the specification of this printer. And under extrusion and over extrusion, so my professor will answer some questions. Like if it is so much difficult here, I don't answer. So
Yeah, if
uh,
it's okay, I'll add a few comments, but you know, let's get Christopher's question.
Well, thank you. Although I can wait if you want to address the other ones first in the chat, if that's what you prefer.
Sure, sure. So I may kind of bounce some of these back and forth off of Moment, but for those who don't know me, I'm Robert Kelly Bradley. I'm Moment's thesis advisor, and I'm assistant professor at Lamar University. So just looking at the chat, I believe the question about the units, decimeter units, came from your density measurements that you gave on, I think, the second or third slide, and I believe that's correct. I believe it was kilograms per decimeter squared.
yeah, the PETG properties,
Or
decimeter cube,
cubed,
yes.
cubed, of course, cubed, yes.
Yeah. The density, yeah, it is actually the properties. So yeah, here I missed it. The kg
Yeah.
per decimeter cube. Yeah, I say meter cube. Yeah, okay.
And Sajid, these are specifications. Are these, did you actually measure these properties, or are these specifications?
It is the specification. I didn't measure it.
Okay,
Yeah, so
yes.
it's from the samples. Like they have the chart, so I just copy it here.
Yeah. And you can see on the bag where we purchased the samples from for traceability there. So just I think probably let me say a few things that may kind of help address some of the other comments in the chat. Sajedul is really presenting work over two master's thesis. Some of the work was with another student who I was hoping could join us, but he wasn't able to make it. Momin Jordan, who did a great job, just like Sajedul has done. But what we found initially is that we were having a great deal of trouble getting dimensional accuracy with our prints. And so originally we were actually looking at coming up with a test object to print on, kind of like, oh, now I forget the name. You guys will know, but the little tugboat that's kind of the classic challenge print item. And so we looked at, various different complicated structures, but in the end, what we realized is we were having such a challenge that we needed to just go to the most basic structure, a cube, and be able to get parameters that would print it with good dimensional accuracy. And then once we got there, to try and optimize those parameters. So, Sajedul, could you go to the slide for the P1, the graph of the P1 parameters versus the print? Yeah, that's fine. Either one of them. So one thing that we should probably point out is that this is actually a small fraction of the actual prints that we attempted. Essentially, each dot on here represents one single experiment, and there was a lot more. But these are the ones that produced a cube that didn't really have any catastrophic failures. They weren't slumping to one side. They didn't have gaps. They didn't sort of have bubbles and things like that. So, all of these, even the ones that have relatively low P1 values on this chart, are all effectively successful prints. And our goal was to try and find what is the optimal parameter, and how does that change as we increase the print speed? Because what you probably notice here is we're printing really slow. But that was just kind of the parameter space that we landed in to get these cubes printed successfully, and so that's what we had explored. And so we actually came up with, I think, 5 or 6 different parameters, like the P1 and P2 parameters, to try and characterize the geometry where we could reduce all the things that we saw in terms of the shape of the cube, to try and reduce it into one numeric value so that we could create these graphs and then try to fit curves to them to optimize them. And you can see that they're pretty noisy, and I think some of the comments kind of addressed those questions about being noisy and outliers and things like that. We tried to address that by doing many replicate experiments, and the fit lines on there, which are a little hard to see, but that was kind of the main takeaway we felt, was that each of those colored fit lines kind of represented, what we would expect in terms of the geometric accuracy based on the print speeds and flow rates. And then you can kind of, in most cases, find, it's a polynomial fit. So in most cases, there's kind of one global or maybe local maximum, but there's kind of one theoretically best point to try and set your speed or set your extrusion, your flow rate, your extrusion rate. The flow rate is the volume of polymer coming out of the nozzle. And so there's kind of for whatever print speed, there's kind of an ideal flow rate to choose.
Could I just jump in with a question about that, please?
Please. Yes.
So in fact, you kind of answered my question when you mentioned optimal, because maybe that was the missing thing when I read your diagram, because, I was the one that commented, I thought those 2 outlying points maybe were skewing the interpretation of the results. But outside of those ones, they appeared relatively tight, and I was then wondering why you fit parabolas instead of linear or constant averages. So I think your point about the optimal is good, but nevertheless, is there a theoretical basis for that as well? Is that why you chose that, or how did you? Because if I were just looking at the data as a scatter plot, it's not quite obvious that there would be that maximum point.
That's a valid point. And no, this is all empirical. In fact, the parameters that we came up with, to the best of our knowledge, we invented those parameters, and we were just trying to figure out a way to represent, the geometry, to see, how different features, like how the top face of the square, how symmetrical it was, how the whole cube was symmetrical, and experimentally try to look at the data and see if we could find an optimal position. We were thinking that we may be able to, once we kind of have this data, to come up with some sort of theoretical model. But as you pointed out, it's a little bit noisy, so it's actually kind of hard for us to know for sure what the theoretical basis would be, and quite frankly, even our fits here, our polynomial fits, kind of are a little, they're not uniform. You can see that in a way the blue and yellow lines kind of seem to do what we'd expect. They have kind of like
Yeah.
a hump in the middle, but then the orange one is very broad and kind of suggests maybe it doesn't really matter that much.
I'm wondering if the use of flow rate is more of a proxy for something that represents maybe a thermal effect of relative cooling on deposition or something of that nature. Has that been something you guys have thought about as maybe the underlying reason why this phenomenon is happening?
Yeah, absolutely. And that's been kind of our underlying driver. In terms of choosing the print parameters because and you guys could probably have knowledge that you could share with us, but as kind of naive users, we started with some of the test objects that came with the printer, like the MOI. And what we found is that everything would just slump on us. The first layers would be very nice, but then as it went up, you'd start to see the layers become wavy, and then it would kind of
Mm.
collapse. And so, our assumption was that we were just printing too fast, and the polymer was still molten.
Mm.
And so we were basically experimenting with different parameters to see, how quickly we're depositing that material. So I think it's certainly true that the flow rate is, and the speed as well, are kind of proxies for, the heat in the sample.
Mm.
And one of the challenges that we've kind of have with using this data is that, the size of your sample, the cross-sectional area of your layer is going to play a role too, because for larger samples, even if you print quickly, you're going to have plenty of time for the previous layer to cool down before you print the second layer. So in terms of the value of this work, it might not be as useful to you if you are printing large structures
Mm.
where everything's going to cool off and there's really no issue. But even
Mm.
for large prints, it's likely that you're going to have a small feature where that might become a problem. And these cubes are 1 inch by 1 inch by 1 inch cubes. So
Mhm.
they're not super small. If you're making a large structure, I think it's likely that you might have something of that size scale within
Mm.
it. And so you might consider, if you're doing rPETG, you might consider, looking at these graphs to decide what you're going to choose for your flow rate and your print speed. Now, one thing I'll ask Sajedul to talk about, because he actually understands this much better than I do, is that you can't really dial in the flow rate directly, at least not in the configuration that we have. We kind of have to get to it in a roundabout way. And Sajedul, could you explain how like if you want to have a specific flow rate, how you get that?
So this one,
Well, I mean, I think this was more of your theoretical calculations, but how does it go back to the there? It's a factor, right? Like if you go to the I think the previous slide where you have the parameters, the print parameters. Yeah, over here you have the extrusion multiplier. I think that extrusion multiplier is actually how you translate it into the printer, right?
okay. Yeah, so it is like when I am doing the work on flow rate calculation, I try different extrusion multiplier, 1, 1.2. So based on that, so when I was printing 1, I got some results in my experimental sample, like timing, like I show the theoretical calculation. So then it was much more like 50% of the actual simplified 3D flow calculation. But then I try to fix it on 1, and when I give the 1, then the extrusion would come 2.1 on the software. Then based on this, I found these calculations, all of the things like I measured the timing and everything. And I have 3 or 4 samples on this, and they are 90 to 95%. It is just one calculation what I have showing here. So, so my understanding is the extrusion multiplier. So if we fixed it on 1, then the printing is going like the flow rate is like more accurate. But when we manually change it or vary it, then it's little bit different. Like I don't get that. Like so that's why I'm using the 2.1 millimeter extrusion weight, which is actually come when I give the extrusion multiplier 1.
Yeah, so it's unfortunately there's a little bit of work involved in terms of selecting your flow rate, and I believe it also depends on the print speed that you select as well. Isn't that correct, Sajidul?
Yeah, I also change, yeah, print
Yeah.
speed. Like print speed, when you change the, it is actually the flow rate is come with from the print speed, but extrusion width, it is come from the extrusion multiplier. So if I use the like extrusion width, like extrusion multiplier 1, then it gives the extrusion width 2.1 millimeter, and other two sample like the layer height and print speed, it just change. So I am changing the 7, then it will come like 20 point something based on this. Then I have the, uh, I print some similar kind of sample, then it gives like 19 or 19 point something. I have the data of that. So this is actually the extrusion multiplier 1, but I set it to 1. But if I vary it, then I have like it is like the percentage of difference is like 50%, 60%. We have also that data also in my book. So that's why I am trying to like do the printing in like 1 extrusion multiplier will be 1. So although we can vary it in the simplified 3D we have.
Right. So those were kind of the comments that I wanted to share, and I'll turn it back over to Sajidul if there's any other questions.
Well, it looks like we might have hit all of the questions with the recording on. So with that in mind, we'll go ahead and turn off the recording. But know if you're listening, you're always welcome to present or ask us to reach out to someone that you would like to present or should attend.